All right, this is Force 4.1. This is the introduction objective to force. This objective says 4.1, explain that force is a vector quantity expressed in newtons having both magnitude and direction. 4.1a says to state that 1 newton of net force will cause a 1 kilogram object to experience an acceleration of 1 meter per second squared. A newton can also be represented as a kilogram times meters per second squared. A spring scale can be used to calculate the force on an object. So first what we're going to do is we're going to review just a little bit that first statement. We know from motion that scalar quantities are quantities that have magnitude only, or just the amount. Things like time, 12 o'clock p.m., temperature, 32 degrees Celsius. Those are all just scalar quantities. They include a magnitude. A vector quantity, however, includes both the magnitude as well as a direction. And in this particular case, force is considered a vector quantity, which means that it does have to include a direction. Now, when we're talking force, oftentimes if people explain force, they say, oh, it's a push or a pull, which is wonderful. Totally agree with that. Push or a pull, good, solid definition. However, it is important to know that it's a push or a pull that is resulting in an object's interaction with another object. Later on in this unit, we're going to talk about exactly what that looks like, but it's important for you to understand. Okay, so this objective also says that force can be expressed in newtons. Kind of like velocity and acceleration, where they have specific units, velocity being meters per second and acceleration being meters per second squared. Force has a very specified unit. Newton. I think we're all familiar with Sir Isaac Newton and his little discovery of force, or his so-called discovery of force with the apple in the tree goodness, which is a lovely tale that many people tell. But I think it's really important for us to understand what a newton really is. The second part of this objective says to state that 1 newton of net force will cause a 1 kilogram object to experience an acceleration of 1 meter per second squared. And newtons can be represented in kilograms times meters per second squared. So basically what this is telling you is that this little unit here, the newton, is the amount of force. This little unit here is the mass of the object. And this little unit here is the acceleration of the object. And you can see kilograms, unit for mass, meters per second square, unit for acceleration. So what they're really trying to tell you here is that if I had 1 newton of force, that means if I applied maybe a push of 1 newtons on a 1 kilogram object, then that object would then accelerate at a rate of 1 meter per second squared. So if you look at this in a different way, if I had 2 newtons of force, so I'm applying a push of 2 newtons, twice as much as before, but I'm still applying it on a 1 kilogram object, my object would then accelerate at a rate of 2 meters per second squared. So more push, same mass, more acceleration. If I had tried to apply maybe the same amount of force on something that is a little heavier or more massive, then what would happen to my acceleration? My acceleration would then decrease. So you can see that there is a definite relationship between the newtons of force, the mass of the object, and the acceleration of the object. And what's really cool about this is if you take a look at the breakdown, force equals mass times acceleration. Spoiler alert, that is really Newton's second law, the relationship between force, mass, and acceleration. So the Newton, while representing how much push or pull you are applying to that interaction of objects, also has to do with the mass of the object and the acceleration of the object. All right, the last part of this objective here says that a spring scale can be used to calculate the force on an object. So I just wanted to give you a little intro to the spring scale. We're going to be using these during class, but I think it's important for you to see exactly how to read these guys. You'll notice that this particular spring scale goes up to a setting of 2.5 newtons. And 250 grams. So essentially what we're doing here is if you take your little spring scale and you maybe pull down on it, maybe I attach an object to it, you can see exactly how much force is being put on that object. If we simply hang an object from the spring scale, we're allowing that object to then have an interaction with Earth, and Earth's gravitational force. So even though you might not actually physically be pulling on the spring scale, as long as there's some interaction, for example, with Earth, then there is a force being applied. And this little spring scale allows you to measure exactly how much force you're applying. There are various types of spring scales that you can use depending on the objects that you're measuring. And like I said, in class, we're going to have a little hands-on experience with this. I hope you enjoyed my little presentation of Force 4.1. Let me know if you have any questions.